In this clip, we discuss a meaty result. This is actually a deep one that has all sorts of implications and stories to go along with it. Let's start with a definition. So for a linear map from V to W, the rank of T is the dimension of the range of T. And so that's one definition, boom. And the nullity of T is the dimension of the null space. So now we have the fundamental theorem of linear maps. And so this is Theorem 3.22 in the book. So suppose that we have a finite dimensional a finite dimensional vector space V and a linear map from V to W. Then the dimension, well, actually, hold on. Then the rank of T is finite, and the dimension of V is equal to the rank of T plus the nullity of T. And so for this reason, this is often called the rank nullity theorem. And in fact, I've always heard this referred to as the rank nullity theorem. And the fundamental theorem of linear maps is something a little bit even bigger and better. This one we're looking at right here is sort of a pale shadow of what's really going on. Let's take a look at the structure a little bit deeper. So I'll come back and I'll prove this theorem in the next clip, but for now, I just want to discuss it. So by 234, so this one said, that was the proposition that said that every subspace is a direct summand, right? So given a subspace U of V, V can be broken down as U direct sum something else. So V can be broken down as the direct sum of the null space of T plus something else, which I'll call R for mysterious reasons to be revealed in just a second. And we also have that the codomain W is broken down as the range of T orthogonal direct sum something else, which mysteriously we've called D for the moment. So this is for some vector spaces R, which is a subspace of V, and D, which is a subspace of W. Okay, so we know that these decompositions occur by that theorem that we saw a while back. And so what does that look like? It looks like this. So all kinds of good stuff going on here. So this is my depiction of the linear transformation of the linear map from V to W. And so I've broken down V as this direct sum here between the null space of V and R. And so you can imagine this is my feeble attempt at trying to illustrate V as a copy of R4. So assume that you've got stuff that's in this plane and stuff that's in this plane here, and everything's going different directions. Same thing over here. So over here I've got W, and it's broken down as the direct sum of the range of T and D. Okay, but there's a bit more to it than that, and it's really easiest to understand if we look at this in terms of a linear map that's being defined in terms of matrix multiplication. So suppose that our map here is actually given by multiplication by A, where A is some m by n matrix, and V is secretly Rn, and W is secretly Rm, and we'll carry on from there. Okay, so let's see what we've got. Now, over here with R, what R really is, R is the row space of A. So all linear combinations of rows of A. Meanwhile, over here, the range is the column space of A. So you might remember from your linear algebra class that anything of the form AX is going to be a linear combination of columns of A with coefficients given by the entries of X. So the column space of A, that's all linear combinations of columns of A. All right. And what else do we have here? Well, we've also got, let me find a good color. So multiplication by A is going to go in one direction. Multiplication by A transpose is going to define a map from Rm to Rn. And so it turns out that over here, D, this is going to be the null space of A transpose, which corresponds to the dual map of T, which is a big important thing we'll talk about in an upcoming section. And so the column space of A, that's the same thing as the row space of A transpose. And the row space of A is the same as the column space of A transpose. So we've got everything going on which way to Sunday, back and forth. All right. The main point out of all of this discussion here is that these two blue planes here and here are going to be essentially the same. So they're going to have the same dimension, and up to like a relabeling of the bases, they are going to be the same. So in other words, what I mean by same, this is a loaded mathematical term for same here. These guys, there's going to be a bijection between them. That is a linear map. And so they're going to have the same dimension. And from the point of view of linear algebra, they're going to be indistinguishable. So if I take the linear map T and I apply it only to vectors that live in R, then that restricted map will be injective and surjective onto the column space over here. So there's a one-to-one correspondence between points of R and points of the range of T. All right, that's the big, whole, hairy story lurking underneath all this. And I thought it might be a good idea to explain some of that. Now, you don't have to remember all of this for now. We're going to talk about matrices and transposes, and we'll even talk a little bit more about the fundamental theorem in the clips to come. But the first time somebody writes down that the dimension of V is equal to the rank plus the nullity of a given transformation, it looks weird and mysterious and like, why the heck should that be true? But once you have a little bit more of this picture, it starts to become very plausible, and you're like, okay, that's kind of what's going on here. And then if you see that V is the null space of T direct sum this row space widget right here, and in fact, when we look at matrices, since Fn has, or Rn rather, has an inner product, a natural inner product on it, we'll actually see that this is orthogonal. Well, you'll see that if you're around for 406. let's see that that's orthogonal. So every vector that lives up here in R is perpendicular to every vector that lives down here in the null space. And so now if we take this decomposition and we just apply the dimension to both sides, then we get the dimension of V is equal to the dimension of null T plus the dimension of R minus the dimension of the intersection by a previous theorem that we saw. But this is a direct sum, so that part is equal to 0 and disappears. And that's where you get the rank nullity theorem.